Good morning, and welcome to our actually second lecture on inferential statistics. Let's just review a little bit from last time. We said statistical inference is a set of procedures in which we take sample information, we try to make sense out of it in terms of how it relates to the population. We're attempting to estimate population parameters by using sample statistics. We said that what this is really about, as you will see in a little while, are decisions. There's a likelihood that a decision is correct, a likelihood that our decision is incorrect. Especially with decisions where we're absolutely certain of that fact. There's a small chance that my car might not start when I go out to it. We said that there are three inferential statistics. The first one being point estimation. We said that point estimation is a situation where we take some sample statistic and we automatically conclude that it's the corresponding population parameter, period. So it's kind of a no-brainer. It's in chapter 7, and they give it about a half a paragraph, that's all. We said the other day that inferential stat number 2 and 3 are much more involved because the underlying basis for 2 and 3 is this mathematical theorem called the central limit theorem that's actually thought of as the underlying foundation for inferential statistics as we know it. And the central limit theorem puts forth the idea of taking this infinite amount of randomly selected samples of a fixed n, therefore computing an infinite amount of sample means, plotting those sample means into a distribution. This distribution is relatively normal. If we were to compute a mean of those means, it would equal mu, the population mean. And the dispersion of all these infinite amount of sample means around mu we call the standard error of the mean. So we said the other day that the standard error of the mean is to this theoretical sampling distribution of the mean what the standard deviation was to the frequency distribution back in descriptive stats. So what the central limit theorem puts forth, and that's, again, it's pretty much the focus of chapter 7, is this idea of the sampling distribution of the mean. The sampling distribution, this infinite amount of sample means, with the mean of the means being the population mean, the dispersion of those means around the population mean equal to the standard error of the mean. Armed with this knowledge now, we looked at inferential stat number 2, interval estimation. We said this is the stuff of chapter 8. Your homework was to look at that, both 7 and 8. We compute confidence intervals. This interval estimation is all about estimating a range of potential sample statistics given one set of sample statistics. What would the range of sample means be if we were to replicate this scenario an infinite amount of times? And we come up with this entity called a confidence interval, which tells us the likelihood that the means will range within a certain interval. The other day we computed a 95% confidence interval, so we could estimate between here and here with about 95% confidence. We said, though, that confidence intervals, interval estimation is kind of a secondary thing, though, in the grand scheme of scientific research. What is primary is number 3, hypothesis testing, kind of like a burger and fries. When you go order a hamburger, you're really ordering that meal for the meat and everything else that goes with it. That's this. Fries come with it. That's kind of secondary. So in any research article, scientific research article, you see the results of the hypothesis test reported first. And then they just secondarily say, oh, yeah, and by the way, blah, 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 confidence interval. So this is the meat of what we're doing the rest of the semester. And actually, the rest of the semester, we're going to have 3 exams just on this topic. This is really huge, all right? What is a hypothesis? It's a statement. So for every research question that we have out there in the scientific world, we have a corresponding hypothesis. So a hypothesis is a statement or a claim, could come in the form of a belief. And we test these statements about a population parameter, whether or not those statements are true. We provide statistical evidence to support or not support the truth of these statements. I have a question. I have a research question. Will our class score higher on exam 2 as opposed to exam 1? Question mark, right? That's a question. I have a corresponding hypothesis that fits that question, just like plug-in, just it fits. Corresponding hypothesis. Our class will score higher on exam 2 as opposed to exam 1. That's the statement. It corresponds to the question. Hypothesis testing is by far the most widely used set of inferential procedures in science. Hypothesis testing these statements and providing statistical evidence in the form of hypothesis tests to either support or not support the plausibility or the truth of these statements. We have more terminology. Have we done a whole lot of math? No. Statistics uses math, but it's really a language. We have this thing called P. And we're going to be using P the rest of the semester. I want you guys to think of P as the region. This is a region. I want you to think of it as a region in the tails, the region beyond a test statistic's critical value. We learned what critical values were the other day. The region beyond a test statistic's critical value. So the P is the region beyond test statistics critical value. Think of it as the region in the tails, the P region. Now, just a few minutes ago when I was putting forth that hypothesis, our class will score higher on exam 2 as opposed to exam 1. What I was essentially doing is putting forth what we call a one-tailed hypothesis. Also called a one-tailed test. A one-tailed hypothesis predicts outcomes will fall in one direction only. The research subjects overall will lose weight as a result of the health and wellness program. Would be an example of a one-tailed hypothesis. Predicts outcomes will fall in one direction only. This one-tailed hypothesis is called a directional test. It's called directional. If I were to say, on the other hand, you know what? Our class will either score higher or lower on exam 2. Our class will either score higher or lower on exam 2 as opposed to exam 1. I would be putting forth a two-tailed hypothesis. also called a two-tailed test. The two-tailed hypothesis predicts outcomes will fall in either direction. As a result of the health and wellness program, the research subjects will either lose weight or, you know what, they may even gain weight, I don't know. In reality, this is a lot more of a realistic scenario, because in reality, on exam 2, you guys are either going to score, in terms of your mean, you guys are either going to score higher or lower, right? I mean, it's either going to be one or the other. This makes a lot more sense, and in this class, we only use two-tailed tests. In this class, we only use two-tailed tests. I have my reasons for it. At this point in the semester, all I can tell you is this is much more scientifically credible. Kind of like, the best analogy, let's use a basketball example. The NBA. This is the 10-foot, the rim's 10 foot high, right? That's the standard, right? This is 10-foot high rim. This is the standard. But let's suppose the NBA decided one day to make the rim 8 feet tall. What would you think about that? Oh, well, gee, it's easier to score baskets, right? What would you think about that? Kind of sketchy, isn't it? You know, it's not real, this 8 foot, no, it's not legit. It's not legit. This is the standard. This is much more scientifically credible. It's much more legitimate. And you'll see why, maybe a couple sessions down the road I'll explain it to you. You'll see why this is. So we have the one-tailed and two-tailed hypotheses. Now, when I was verbalizing that hypothesis about, you know, our students are going to score higher on exam 2 as opposed to exam 1, what I was putting forth was what we call a conceptual hypothesis. The verbalization. Scientists like to sit around and talk about things. Gee, if we create this experimental group, I wonder what will happen as opposed to its, difference from the control group. I wonder, predicting outcomes and such. And they start out doing this verbally. Then they transform that into what we call a statistical hypothesis. Which is the mathematical statement.
So this is a transformation that goes to a statistical?
Mm-hmm. So for every conceptual hypothesis that we have a corresponding statistical hypothesis. And the statistical hypothesis is nothing more than the corresponding mathematical statement. These statements are, typically all about relationships between variables or differences between groups. Will there be a significant difference between the mean of, exam 2 versus exam 1? Will there be a significant difference? In fact, today, as time goes on, we're going to learn what statistical significance really is. We've heard it in the popular press as we've been growing up. We've heard that term, statistical significance. We're going to learn today what that really means. What it really means. And it has everything to do with what's going on this sampling distribution. That's just a little clue. Okay, I'll keep you in suspense. We're not quite there yet. There are two types of statistical hypotheses that we use, and we're going to be using these the rest of the semester. The first type of statistical hypothesis we call the null hypothesis. The null hypothesis is written H sub 0 colon And just write in your notes, mu equals 63. Just write that in there. This is a typical null hypothesis. The null hypothesis is the statement of no. It's the statement of no difference, no relationship, no effect, not pregnant, you know, whatever. The statement of no.
Is that mu?
Yes, that's a mu. Yeah, it's not an m. Yeah, it's a mu. The population mean, we always write the null and the alternative in population parameter symbols. So these, you know, hypothesis testing is all about population parameters, you know. How sample relates to population. We're going to see that in a few minutes once we start examples, in about 10 minutes. We also have this thing called the alternative hypothesis. Which is the opposite of the null hypothesis. It's the opposite. There is a difference. There is a relationship. There is an effect. So, you know, this is the opposite of this. You know, not pregnant. What's the opposite of not pregnant? Pregnant, yeah. Typically, the alternative hypothesis, H sub 1 colon, I just want you to write mu is not equal to 63. Now again, nulls and alternatives are always written in population parameter symbols. And because we're only using two-tailed tests, class, this is a typical two-tailed null and alternative situation. Look in chapter 9 under the two-tailed tests, examples of two-tailed tests, you will see equal sign, not equal sign. In fact, it's really important for you at this point to really dig into that chapter 9, see what's going on. You'll see a lot of the same things as we're going over in class. The null and the alternative. Now, this is where things start to build in the movie, in our movie. Okay? We have a goal in every hypothesis test we do, and again, there is a hypothesis test designed to help us answer every research question. If ever you're wondering why we're doing this, it's because we're trying to answer a question scientifically. We're trying to answer a question scientifically. For each hypothesis test that we run, we're going to be running them the rest of the semester for the next 2 months. Isn't that exciting? For each hypothesis test that we run, we're going to have a goal in every one we run. The goal in any hypothesis test is to reject the null hypothesis in favor of the alternative hypothesis. And when we have enough statistical evidence to be able to do that, we can conclude that we've detected a statistically significant difference, a statistically significant mean difference, or a statistically significant relationship between variables. So the goal in every hypothesis test that we do is to reject the null. When we have enough evidence to reject the null, we have found statistical significance. Now we don't know quite what that is yet, but hint, it has everything to do with what's going on over here. You're probably wondering now, because you're so astute, you know, you're such great students, probably wondering, gee, how do we reject this null? Well, here's how we do it. We use this thing called the rule. And the rule is synonymous with the critical value approach in our books. In chapter 9, you're going to see what they call the critical value approach. I like to call it the rule. It's a rule we're going to be using the rest of the semester. It goes like this. If a calculated test statistic exceeds its critical value at a given nominal alpha level, we'll talk about alpha in a minute, we reject the null. In favor of the alternative, conclude we've detected a significant group mean difference or a significant relationship. What does this mean? It means that if a calculated test statistic exceeds its critical value either in this direction or in this direction, that statistic that we've computed is considered so rare of an event that it's considered a significant event. Again, if a calculated test statistic exceeds its critical value, either in this direction or in this direction, we reject the null. We have statistical significance. But what is statistical significance? Well, that test statistic has exceeded its critical value. Let's say the z that we compute is 3.25. It's right here. This is considered such a rare event that it is deemed a significant event. Think about rare events in your life. Like graduating from high school, getting your driver's license, getting married, having your first child, buying your first house, whatever. These are all significant events, but they're also rare events. Why? Because they don't happen every day. It's not like, brushing your teeth or going to Walmart or something. These are normal events. They happen a lot. Brushing your teeth is a pretty normal event. Brushing your hair is a normal event. Graduating from college, that's a rare event. Yeah. So if any of these test statistics get out into these regions of rarity, that's what the tails are, the regions of rarity. They are deemed such a rare event that they're deemed a significant event. And that's what statistical significance is. And our goal in every hypothesis test we do is to reject the null. Sometimes we can, and sometimes we can't. So if our test statistic falls out in one of the tails, we reject the null. If the test statistic falls in the middle somewhere, we accept the null. If the test statistic falls in the middle somewhere, we would accept the null or fail to reject the null. Those are the same things. Accepting the null and failing to reject the null are identical. It's just a different way of stating it. So our goal in every case is to reject the null. And we do this by using this thing called the rule. Chapter 9 also introduces what we call the p-value approach. And there's another piece of this rule that's kind of like a different way of looking at things. If p is less than alpha, we'll talk about alpha in a second, reject the null. If p is less than alpha, reject the null. What is this alpha business? Let's talk about alpha. We have this entity that we call alpha, and it is symbolized using the Greek alpha. Small, lowercase alpha, kind of looks like a little fish. Think of a little fishy here. It's the small likelihood class. It's the small likelihood that my decision to reject the null is not a correct one. Or it's the likelihood that if in fact I have found enough evidence to reject the null, it's the small chance that my decision to reject that null was wrong. Just like, when I go out to my car after class, I'm pretty certain that that thing's going to start. I'm real certain that but you know what? I'm not absolutely certain. There's a small chance that it might not start. There's a small chance. I'm pretty certain that when I walk out of that door after class, I'm going to be walking and breathing. There's a small chance that I might walk out that door and keel over and die. You know what I'm talking about? We're not absolutely certain about anything. Except death and taxes. That's an old, No, but you know what I'm talking about. We're never really absolutely certain about anything. Other than, the sun's going to go down tonight. But you know what I'm talking about. In the grand, so we talk about lack of certainty. This is what we're talking about. We're talking about statistical decision making, decisions. Alpha is the small likelihood that if I have indeed found enough evidence to reject the null, that my decision is not correct. Now, there are different alpha levels that are common: 0.1, 0.05, 0.01, 0.001. 05 and 01 are the most common. 05 is pretty much the standard. Alpha 05, alpha 0.05, alpha 5%. The book calls this significance level. So alpha and significance level are synonymous. The 5% significance level. So if I have in fact rejected the null, using an 05 alpha, there's about a 5% chance that my decision to reject the null was not a correct one. And about a 95% likelihood that my decision to reject the null was a correct one. Again, alpha, the small likelihood that my decision to reject the null was not a correct one. Before we run any statistical test, P equals alpha. Before we run any statistical test, P equals alpha. It's going to change. Okay? We compute the test statistic. P is going to end up either less than alpha, in which case we would reject the null, or greater than alpha, in which case we would accept the null. Now, we're going to be working with this the rest of the semester, and we're going to be seeing this visually every single time we run a hypothesis test. But for now, you just need to memorize, every good boy does fine. Okay, these are, if we are musicians, we're learning our scales. These are the basics, okay? And we got to do a lot of repetition, don't we, to really have it sink in. The way we're going to get this is through repetition. And you're going to see. You're learning something, you guys, that most of the population have no idea about. So you guys, consider yourself special. Even though you might be sitting here, maybe a little bored out of your minds, or going, what? I'm introducing all kinds of pieces and parts here. Kind of like teaching you what a carburetor is, what spark plugs are. In a few minutes, we're going to see how this all fits together. We're going to see how the internal combustion engine actually works together. So these are all the little pieces and parts. We're going to be working with all these parts the rest of the semester. As time goes on, if you really put forth the effort, you're going to get it. You're going to see. You're going to become enlightened, okay, so to speak. That's why you're here. It's not easy. If this was easy, everybody would be doing it. It's not supposed to be easy. Okay, it's not supposed to be easy. All right? You give it enough time and effort, it's going to sink in, and you're going to get it. And you'll have knowledge that most people don't have. That's pretty cool. I'd like to talk about statistical errors, or potential errors in statistical decision making. There are two of them, two potential errors. Type 1 error and type 2 error. Whenever I reject the null, whenever I have found statistical significance, there's always that small chance that I may have made an incorrect decision in rejecting my null. We just talked about alpha. The likelihood that I made an incorrect decision is called the likelihood or probability of a type 1 error. So when I reject the null, it's not to say that I actually made a type 1 error. It's to say that there's a small chance that I may have committed a type 1 error. Type 1 error, or the likelihood of a type 1 error, is symbolized by alpha. And we commit a type 1 error when we reject the null when we really shouldn't have. We commit a type 1 error when we reject the null when we really shouldn't have. The book refers to this as rejecting a true null. And in your spare time, you need to go to pages 381 and 382 of the 6th edition, or 384 and 385 of the 7th edition, to these tables and look at them. You have to really take that chapter 9 and really dissect it. Okay? Now, the committing of a type 1 error is considered a false positive. Does anybody know what a false positive is? How about, does anybody know what the EPT test is? Okay. It's a pregnancy test. If you get a false positive on the EPT test, what does that tell you? It's telling you you're pregnant when you're really not. The type 1 error rate for EPT is about 0.0001. Like for every 100,000 EPTs taken, there is one that tells a woman she's pregnant when she's really not. That's a false positive. You know, claiming an effect that's not there. Claiming an effect that's not there. So there's always a small chance when I have rejected the null that my decision to reject that null is wrong. The actual committing of a type 1 error is considered a false positive. Now, it's not to say when I reject the null that I've committed a type 1 error. No. It's to say that when I reject the null, there's a small chance that I may have committed a type 1 error. There's a small chance that I may have rejected a null when I really shouldn't have. Type 1 error. So whenever we've detected a statistically significant result, it's right in your notes here, there's always a small likelihood, that's alpha, that I made an incorrect decision in rejecting my null. Whenever I have a non-significant statistic, whenever my calculated statistic falls in this mid-region somewhere and I don't have enough evidence to reject the null, so I accept the null, right? This is irrelevant. But there's a small chance that I may have committed a type 2 error. There's a small chance I may have committed a type 2 error. Type 2 error is symbolized using beta. We commit a type 2 error when we fail to reject the null, when we really should have. We failed to reject the null when we really should have. It's also called failing to see an effect that's there. Failing to see an effect that's there. The book refers to this as failing to reject a false null. Bless you. A false negative. A false negative. The EPT test tells you you're pregnant Well, the EPT test tells you you're not pregnant when you really are pregnant. It's claiming, you know, it's detecting a biochemical change that's actually not there. Whenever we have a non-significant statistical result, there's always a chance that I may have made an error in my decision to accept the null. So, you know, in case of the EPT, you know, tells you you're not pregnant when you really are pregnant. The false negative. Now, these are potential errors. You got to remember this. We're either going to reject the null and have statistical significance, or we're going to accept the null and have non-significance. If we reject the null and have significance, this is a small issue. This is a non-issue. If we accept the null, if we have non-significance, this is a small issue. Small issue. This is a non-issue. This is irrelevant. Potential errors in statistical decision making. I have a handout for you. Get that thing out real quickly. Let's see how this stuff works. We're going to be covering 2 hypothesis tests before our next exam. Our next exam will be coming up before you know it. It's time now. You know, it's really time to put it into high gear now in terms of your studying. This is out of chapter 9. Hypothesis test number 1 is a situation where mu is known and sigma is known. Mu and sigma are known. So our population mean and our population standard deviation are actually known. We're attempting to answer a research question. This is always the case. This particular question states, is there a significant difference between our population mean and our sample mean? Is there a significant difference between the population mean and the sample mean? The null would state there's no significant difference between the population mean and the sample mean. The alternative would state there is a significant difference between the population mean and the sample mean. We have a statistical hypothesis test called the z-test to help us answer this question. The whole purpose of this is to answer the question. Provide evidence, scientific evidence that helps us answer the question. Answer this question in this case. Z in this case is our sampling error numerator divided by the standard error of the mean. And we know our standard error of the mean, right, is sigma over the square root of n. Let's see how this all works. Let's use example number 1. Listen very carefully, watch very carefully. A professor is given an exam that for 10 years has yielded a mean of 78 and a standard deviation of 7. So this professor for many, many years has gathered this data, compiled all this test data, computed a mean that he calls the population mean, 78. Then he used the computational formula for variance, took the square root of that and got a standard deviation of 7. So the variance we know would be what? 49, right? His current class of 22, students actually has a mean of 82. His current class of 22 has a mean of 82. We have a research question here. Is he correct in assuming that this class's mean is significantly different from other classes? Is he correct in assuming that this class's mean differs significantly from other classes? Gee, I don't know. What I do know is that it has everything to do with what's going on over here. And what we're going to be doing is making a determination as to where does this individual sample mean fall on this sampling distribution? Where does this individual sample mean fall on this sampling distribution? Class, if it falls way out here or way out here, what's our decision going to be based on the null? And we would reject the null. Everything that happens out in the tails is the rejection scenario. Look in your books. This is called the rejection region. But if our calculated statistic falls in here somewhere, we're going to accept the null and conclude that we have a non-significant difference between x bar and mu. This is the first set of information that we're going to be collecting in these hypothesis test number 1 problems. When you're doing this, list all these. Proceed to step 2. We're going to state the null. In this case, the null, h sub 0 colon mu equals 78. Alternative hypothesis, h sub 1 colon mu is not equal to 78. Mu is something different than 78. We have a mu of 78. Let's put that right here. Mu is 78. Where does the sample mean of 82 fall in relation to this? We still don't know yet. We will in a minute, though. We're going to kind of take care of some preliminary things. Again, this is what we're just getting the data set ready to actually make this determination. This thing calls for an O5 alpha and a two-tailed test. We're always running two-tailed tests. We run a two-tailed test. And actually, the researcher chose a two-tailed test because before he gathered this 22 research subjects, he didn't know whether this sample mean would be above the population mean or below it. Turned out to be above it, but he didn't know that. He picked a two-tailed test just to be safe. We know that before we run any statistical test, p equals alpha. Before we run any statistical test, p equals alpha. In this particular case, our z critical values are negative and positive 1.96. And we need to know why this is. We need to know why this is. If you get your textbooks out real quickly, go to the z-table. Get your textbooks out real quickly, go to the z-table. If you didn't bring your textbook, look on with somebody else. Go to the z-table, negative 1.96. This is very important that we get this right now. Go to a z, negative 1.96. You're going to see the number 0.0250. This means that we have 2.5% area from here back, 2.5% area from here back. This is a symmetrical distribution, so what happens on this side also happens on this side. So we have 95% area from here to here, right? 2.5% area from here back. I made this point the other day. 2.5% area from here back, 2.5% area from here back. We're running a two-tailed test, so the p region is cut in half. Half of the p region is on one side, half of the p region is on the other side. These 196s are cutoff points. They're critical values. 2.5% area falls from here back. 2.5% area falls from here back. 2.5 plus 2.5 equals 5%, or 0.05. So we're operating at the 5% significance level. Chapter 9 will also refer to alpha as the significance level. If z exceeds positive 1.96 or negative 1.96, we have enough evidence to reject the null, right? If z falls in this region somewhere, what would our decision be? Accept the null. Very good. We have a population mean of 78. Let's compute z and see what's going on here. Z equals 82 minus 78 divided by our standard error of the mean. This is going to tell us a lot. In fact, we're going to kind of back into this situation. This is going to tell us a lot about what's going on over here. Standard error of the mean, sigma 7 divided by the square root of 22. Square root of 22 is 4.7. Standard error of the mean, in this case, 1.49. Class, question. Based on this, what does one z unit equal? What does one z unit equal to? 1.49. We're going to treat this just like any other form of sigma or s. We're going to go out addition-wise this way, back subtraction-wise this way. Watch. 78 plus 1.49, 79.49. Plus 1.49, 80.98. Plus 1.49, 82.47. 78 minus 1.49, 76.51. Minus 1.49, 75.02. Minus 1.49, 73.53. We have raw score scale and its corresponding standard scale that we call z. Now this makes things a lot easier, because now all we have to do, where does this 82, where does this individual sample mean fall on this sampling distribution of the mean? Where does this 82 fall over here? Well, look at this. It's right over here. In fact, you know what? The 82, it's about right here. It's going to correspond to a z a little bit less than 3. What do you think our decision based on the null is going to be? Reject. We're going to reject it. This is kind of like just back at, this is like talking to the prosecutor before you go before the judge. You know, you kind of like, the decision is made. Then you go before the judge and, yeah, you know, you're guilty, $250 fine, you know, whatever. But you know what I'm talking about. You kind of like work things out beforehand. So now it becomes a formality. Let's formally run the z-test and make the decision. This is 4, right, divided by 1.49. Z ends up being 2.68. Now we use the rule. We compare the calculated statistic to the critical value. Yeah, you know what? We see it exceeds it in the positive direction. It's about right here, just like we predicted. Therefore, class, our decision based on this null is to reject the null. We reject the null. This z, 2.68, right about here, lines right up with this sample mean of 82. We have determined, we now have evidence that strongly suggests that this mean, again, which corresponds to this z of 2.68, is a rare event. In fact, it's such a rare event that it has been now deemed a significant event. We can now conclude that we have a statistically significant difference between the population mean and the sample mean. Yes?
How do you know that you had enough statistical evidence?
Because that's a great question. How do I know that I have enough statistical evidence? Because we do.
Because it matches up?
Because this z of 2.68 corresponds to this mean of 82 is right here on the sampling. This is a rare event. This z, which corresponds to this mean, is a rare event. Such a rare event that it's now been deemed a significant event. Z's of this magnitude are rare. Z's of this magnitude are pretty common. You know, this is the guy that drives the Toyota Corolla. This is the guy that drives the Lamborghini, okay? This is the guy that's, you know, 5 foot 10 inches tall. Pretty common, right? This is the guy that's 8 foot 6 inches tall. Pretty rare. Rare events are significant events.
What about the 80.98? How will we consider that? Like,
This is just...
It won't be rejected, right?
Yeah, this is just the raw score at the second standard deviation. It's just z of 2 corresponds to 80.98. That's just, yeah, that's just a part of the raw score scale.
I have a question.
Yes?
What if the mean, like the sample mean, was 80.98? Would it still be significant because it's like still more than the critical?
Yeah, exactly. So the 80.98 would fall right here. It's a little bit larger than 196. Yeah, yeah. Question? Yes?
For it to be, like it's mean equals 78, so we, how do you know, because if it's not equal to it, it can still be,
So
the null.
So we rejected this statement, thereby accepting this statement, which states that mu is something other than 78. In fact, we might have a new population mean. What might that new population mean be? It might be 82, it might not be 82, but it's certainly not
78.
Yeah. What I want you to get from this right now is the whole notion of statistically significant difference.
Okay.
And at this point, we've determined we have a statistically significant difference between x bar and mu. This distance has been deemed large enough that has been deemed significantly large enough. The p region got smaller. If p is less than alpha, we reject the null. What do I mean by this? This is what I mean. Before the analysis, our needles were right here and here. 2.5% area from here back, 2.5% area from here back. But guess what? Z changed. Z turned into 2.68. This needle stayed right here. Therefore, this area remained at 2.5%. But this needle shifted from 1.96 over to 2.68 and actually smushed this p region. It reduced it to something less than alpha. Class, go to a z of 2.68. Tell me what that area is. It's 0.999 something.
0.9963.
Now get on your do 1 minus 0.9963. 0.0037. P now is actually equal to 0.0287. P has been reduced from 5% to 2.87%. Is 2.87% less than 5%? Yes. If P is less than alpha, reject the null. What this means is that this area remained at 2.5%. This area, however, was reduced because Z shifted from 196 to 2.68. This needle went over to 2.68, actually made this region now smaller. It's actually about 0.37%. Totaled to be 2.87% or 0.0282 proportion. If p is less than alpha, reject the null. That is the p-value approach. There's two approaches. They're the same, but a little bit different. Our calculated statistic exceeded the critical value at a given nominal alpha level. We made the decision to reject the null. And also, in doing that, p became less than alpha. The p region was reduced to an area less than 5% of the total area in the p regions. We have a question. Let's answer it. Is he correct in assuming that this class's mean differs significantly from other classes? Yeah. But you're wondering, well, why? Well, this is why. Because this z, which corresponds to this sample mean, again, is considered a rare enough event to be deemed a significant event. We rejected this statement, thereby accepting this statement, which states that the population mean, differs significantly. It's something other than 78. It may be 82. It may not be. We rejected this null. However, there is a small chance that my decision to reject this null is not a correct one. I rejected with some pretty high certainty, with about 95% certainty. There's still a small likelihood that I may have made an incorrect decision in rejecting this null. So the likelihood I committed a type 1 error is 5%. So I rejected with some pretty high certainty, with about 95% certainty. The likelihood I committed a type 2 error is kind of a non-issue, in this particular scenario. Okay, let's go on to the next example. Go to the next example, draw a sampling distribution real quickly. And like I said, class, as time goes on, this will start sinking in. We're going to do this so much that you're just going to get it. This next example is out of marine biology. Our friend Travis, he's a lobster fisherman. Travis does research with the marine biology research team. His job is to catch lobsters, weigh them, tag them, and return them to the water. Over the years, the team has determined that the average weight in pounds of the lobsters caught at a particular location is 2.1 pounds, with the standard deviation of 1.8 pounds. As part of an annual survey, Travis catches 27 lobsters with a mean of 3.1 pounds. So again, we have our first set of information, and I'm going to label this step 1. When you're doing your problems in the packet for homework, you do it exactly like this. Just take a deep breath, take it in steps. The first thing you do is draw a sampling distribution. And in this case, we're going to put 2.1 right in the middle. Mu equals 2.1. Is Travis correct in assuming that the lobsters he caught are significantly heavier than those usually found in that location? Well, let's look at the data. It's obvious that, yeah, this sample mean is about a pound heavier than the population mean. I mean, I already know that. The question now becomes, is this significantly heavier than the population mean? What I'm trying to ascertain, where does this individual sample mean, just like last time, fall on the sampling distribution? Class, if this sample mean falls somewhere in the middle, what's my decision going to be based on the null? Very good. Don't ever forget that. Accept the null. If this sample mean, it's going to correspond to some z I compute. If this sample mean falls somewhere in the tails, what's my decision going to be? Reject the null. Very good. Don't ever forget that. This is like every good boy does fine. And the more you practice your scales, you know, and your pentatonic scales, the musicians are talking about, this is how they get good. Repetition. The more ground balls you pick up, the better you get at it. You just get used to it. Okay? We're going to set the null hypothesis h sub 0 colon mu equals 2.1. The alternative hypothesis h sub 1 colon mu is not equal to 2.1. Again, we have a two-tailed null and alternative scenario. This thing calls for an O5 alpha and a two-tailed test. Travis picked a two-tailed test because actually before he caught these lobsters, he didn't know whether the sample mean would be above the population mean or below it. Turned out to be above it. That's fine. He didn't know that at the outset. Picked a two-tailed test just to be safe. Remember, a two-tailed test predicts outcomes will fall in either direction. We know that before we run any statistical test, p equals alpha. It's going to change. P will either be less than alpha, in which case we reject the null, or p is going to be greater than alpha, in which case we accept the null. Our z critical values, again, negative and positive 1.96, and it is of utmost importance that we know why this is so. We have an alpha of 0.5, therefore a p of 0.5, and we're running a two-tailed test. These are our cutoff points. The needles are right here. 2.5% area this way, 2.5% area from this position this way. 2.5 plus 2.5 equals 5, 5%. Alpha is 0.5. The p region is cut in half. 2.5% this way, 2.5% this way. This is step 2. So tonight when you're doing, you know, some practice problems, this is how you do it. This is step 2. Let's take a look at z and see what's going on. Sampling error numerator over standard error of the mean. Standard error of the mean, sigma over the square root of n. The z statistic, 3.1 minus 2.1 over the standard error of the mean. The standard error of the mean is going to tell us a lot about what's going on over here. Let's kind of back into this thing again and get a clearer picture as to what's going on. Then we'll address z formally. Standard error of the mean, sigma 1.8 over the square root of 27. That's 1.8. Square root of 27 is 5.2. Our standard error of the mean, in this case, 0.35. Class, what is one z unit equal to in this case? 0.35. Let's treat it as such. Out addition-wise, back subtraction-wise. 2.1 plus 0.35, 2.45. Plus 0.35, 2.8. Plus 0.35, 3.15. We can just sort of stop right there. Class, look at x bar over there. 3.1. Where does it fall? Where does 3.1 fall on the sampling distribution? A little bit before here. It's about right. About right there. This particular sample mean data point is right here. How about that? What kind of event is that? Is it rare or is it just common? Rare. Looks pretty doggone rare to me. Do you think z is going to be significant?
Yes.
So are we going to reject the null or are we going to accept the null? Yes. Very good. Now let's formally do that. I love it. You guys are doing really well. Now all you need to do is practice, 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 practice. Sets, lots of them. You're going to get really good at this. Z is 1 divided by 0.35. Z ends up being positive 2.86. Let's use the rule and formally do this. We compare the calculated test statistic to the critical value. We see it exceeds it. Again, just coincidentally. Therefore, class, our decision based on this null is to reject the null. Yeah? What happened to the p region again? Yep, it got smaller. If p is less than alpha, reject the null. I'll address that in a minute. Let's answer the question. Is he correct in assuming that the lobsters he caught are significantly heavier than those usually found in that location? Yeah. But why? Well, this is why. Look, Z is 2.86. It's right here. A little bit before it corresponds to this mean of 3.1. We have a rare event. Rare events are significant events. This statistic is so rare that it is deemed significant. Therefore, we have determined that we have a statistically significant difference between the sample mean and the population mean. The distance from here to here has been deemed large enough that it has been deemed significantly different. Now again, there is a small chance that my decision to reject this null is not a correct one. So the likelihood I committed a type 1 error is 5%. So again, I rejected this null with about 95% certainty, which is pretty high. Small chance that I may have made a mistake, though. The likelihood I committed a type 2 error is a non-issue. That would only come into play if I had a non-significant statistic. And again, the p region was reduced to something less than 5%. The needles were right here and here. At the 196s. But Z turned into 2.86. This needle stayed right here. Therefore, this area remained at 2.5%. But this area got smushed. This needle actually shifted from here over to 2.86 and made this region of P smaller. We can determine this region of P. Somebody look up Z. Actually, just look up Z negative 2.86. That'll tell us what we really need to know. It's symmetrical, so it's the same on both sides. Look up Z negative 2.86. Tell me what the number is.
0.0021.
0.0021. P is now equal to 0.0271. Is 0.0271 less than 0.05? Yeah. Is 2.71% less than 5%? Yeah. If p is less than alpha, reject the null. And this is the p-value approach. They're both the same thing. They just sort of approach the situation from a different angle. Now, we've done a lot today, and you guys have done a really good job. I'm going to dismiss you in about 2 minutes. Just be quiet. I would like you to finish the problems in this packet. And this is how you do it, just like we did today. Read the problem, extract this information out of the problem. It's identical. In terms of, get this information. This is step 1. Then do step 2. The next problem uses an O1 alpha, two-tailed. What are our critical values going to be? O1 alpha two-tailed. What are our critical values going to be? It's going to be the 2/5/8. 0.5% this way, 0.5% this way. 1/2 plus 1/2 equals 1%, added to the 99% equals just about the whole area under the curve. So the 2/5/8 will be our critical values. List all this information with critical value positive and negative 258. This is step 3. This is step 3. Then run the z-test. The z-test is step 4. And then step 5, make the decision and interpret. I will see you guys next time, and we will pick this up. Have a great day.